is that it's a way to discover patterns in existing data, right? And then to reproduce those patterns when classifying new inputs. Yeah, that sounds like pretty close to a textbook definition of machine learning. But when we're talking about any of these domains where we're making decisions about people, where does the training data come from? The training data ultimately reflects human society. It is collected based on the behavior of police, based on judges' past decisions, and so on in the criminal justice context. And so we should expect that if the training data reflects human society, then machine learning techniques are going to capture the biases and stereotypes and historical prejudices that are reflected in that data. Right? And so what I want to emphasize here is that this is going to happen in the criminal justice domain. This is going to happen when we're using predictive algorithms for hiring based on our past data, based on past decisions that humans have made. And so I want to encourage you to see bias in machine learning as the rule rather than the exception. I could give you specific examples, and I'm going to give you several specific examples throughout the talk. But the thing I want to emphasize, the reason I'm not giving you examples now is because I don't want you to think these are one-off cases where these issues have come up. I want you to think of this as fundamental to machine learning. When you're using it to make decisions about people, the data is going to reflect societal biases that exist in our culture today, and these algorithms are going to pick them up and reproduce them when making new decisions. And I will get to specific examples. Yeah, so one question we can ask is, why is this partly our responsibility? That is the responsibility of data scientists and people working on machine learning. Why is it not enough to say, whoever is using these algorithms out there in the criminal justice system or in hiring or insurance, loans, housing, so many different applications? Why is it not enough to say, if that person puts in unbiased data, then the algorithms are going to make unbiased decisions? That's a reasonable point of view, but let me also point out that there are several reasons to study this specifically in the context of machine learning. There are reasons to think that these problems become different in the machine learning context, and actually in very interesting ways and intellectually interesting ways, in ways that are leading to new research. So here is the first reason. When we define the accuracy of a classifier, for example, we might look at an overall metric of error, right? How many errors did it make on the entire population? Usually, the way that we learn machine learning in textbooks and in classes, we don't break down that error into different demographic groups. If there's one demographic group that's a 90% majority and another one that's a 10% minority, we don't ask, is the 5% error of my algorithm evenly distributed between those two groups? Or is that 5% error entirely borne by the 10% minority group? In other words, is my algorithm essentially making random decisions for the minority group? The way that we usually measure accuracy in AUC and so on, we just wouldn't know the difference between these two scenarios. And yet, of course, when you look at the impact that the algorithm is going to have on society, these two scenarios are enormously different. Now, is this just an academic concern, or are there fundamental reasons to think that the minority group might bear more of the error in a typical machine learning situation? What do you think? So think about the fact that by definition, for the minority group, there is less training data, right? And of course, we know that machine learning works better, is able to better model the population when there is more training data. And so if the data distribution systematically differs between the majority and the minority group, which it turns out is often the case in practice, then we should expect that systematically there's going to be more error for the minority group. So that's one reason why there's something new when you bring these problems to the context of machine learning. Another reason is that all of this, point number one is true, even if there are no biases in the data itself, even if there are no measurement biases in the data. And yet, when you look at the real world, data biases end up being inevitable. And so it's not enough to say my algorithm is going to work well if the data is unbiased. That's not going to be a very useful algorithm. What society is demanding today is for machine learning technology to incorporate ways of correcting for or mitigating the inevitable biases in the training data. And that's not a question to which the machine learning and data science community has paid a lot of attention for the last several decades, and that is starting to change now, and that's why there's a lot of research going on on how can we do this. And a third reason is, think about it this way. A fundamental assumption in machine learning is that your training distribution and your test distribution are the same, right? Does that make sense? Does that sound familiar? That's something we learn in textbooks. Now, where does your training data come from? It comes from the past. Where does your test data come from? It captures future instances on which we want to make decisions. Yeah, so we've assumed that the training distribution and test distribution are the same in the way that we've learned machine learning in school. But what people want in real life is they want to use machine learning to learn from the past, but not necessarily reproduce the past when making future decisions, because of the acknowledgement that inevitably there are going to be these data biases in criminal justice and hiring. And those biases inevitably exist because the way that humans have made decisions for decades and for centuries reflect these biases. And so we don't necessarily want to pick up those biases in making new decisions. This calls for new science. We genuinely don't know how to do this today. And that's going to be at the core of one of the hard problems that I'm going to propose in my talk. And there's a fourth reason as well why these are new and interesting problems, which is that AI technology, the way it's sold today, sort of has the veneer of objectivity. Right? This is algorithmically pure and perfect. It's going to make neutral decisions. So you can take it and use it for criminal justice, for hiring, for loans, for housing. However, that almost never ends up being the case. So there is perhaps even a greater responsibility for data scientists developing these systems because of the way that they're marketed and pitched. So let me tell you just a little bit about the concerns of this field and its history. It turns out that one of the earliest papers on this was called Bias in Computer Systems by Friedman and Nissenbaum. And they didn't talk about machine learning specifically, but they anticipated a lot of the concerns that have emerged today. But for a long time, people weren't paying serious attention to these issues. If you look at the academic literature and you look at when these issues started getting taken seriously, let me show you a funny chart by Moritz Hart. Right, so there's been a kind of an explosion in the last couple of years or so. Something has changed. There is an acknowledgement that these issues are super important. Another example of this is a couple of years ago, tech companies just didn't really want to engage with the public on these concerns about fairness and accountability and transparency in machine learning. But today, in fact, last week at the FabStar conference, Google, had something like 1/10 of the participants overall of the whole conference. That situation has changed enormously. There's a demand from society, and that in turn has led to this complete 180 from tech companies, and acknowledgement that these issues are critical and important as they put machine learning into more and more products. So a lot has changed recently, and there's a lot of interesting research going on. And I think it's coming at the right time. In fact, I want to say that it's almost too late. I want to point to some applications of machine learning that I personally feel are very poorly conceived and are just perfect vehicles for capturing and perpetuating this bias that have become very successful commercially. Let me give you one example. A company called HireVue. Here's a quote about what, sorry, this is just a teaser for what this talk is going to be. Where is this HireVue slide? The HireVue slide is not showing up, so let me read from the slide here that is not showing up for some reason. HireVue is a company that uses voice and face recognition software. This is employed in a situation where a candidate is required to do a video interview. And this AI technology analyzes the candidate's facial expressions and body language and speech patterns and compares that to previous candidates and how those candidates have performed at the company, and uses that to automatically screen candidates based on video interviews for managers to then invite for interviewing or whatever. Right? So think about what is happening here. The important critical questions are not being asked. What reason do we have to believe that somebody with one speech pattern or another, with one body language or another, is going to be better at doing a particular job? Instead, there is this assumption that let's just gather all the data that we can and throw machine learning at it and pick out, basically make future decisions that are as similar to our past decisions as possible. I claim that this type of application of machine learning that HireVue uses, there's no signal to pick out in the data. It's essentially a bias perpetuation engine. It's a way to make decisions in a way that picks out the biases that employers may have had in the past towards people with certain accents or certain body language. So that's kind of the situation that we're in today, this kind of really unthinking application of machine learning. And there's a pushback that's going on. And so that's what has led to the recent emergence of this fairness in machine learning community. There's a lot of research going on. There's also a lot of advocacy going on of how can we mitigate these algorithmic biases. So that's kind of the setup. That's what's going on in the community. Hopefully that makes sense, and then I'll get to the technical part of the talk. Excellent. So the points that I want to make in terms of the hard problems, I want to point to two hard problems, and you're going to see this in detail. One I'm calling the fairness impossibility theorems, and the other is an acknowledgement that some biases might be things that we want in the data, and some biases might be the result of prejudice that we want to really avoid, and there's no way to algorithmically tell these apart. So the end result of these, here's what's the end result of this. The way that computer scientists and data scientists and statisticians have approached this problem is to say, okay, we acknowledge that there are biases in the data. We're going to come up with these fairness constraints and make sure that the algorithms that we build are neutral according to those fairness constraints. Or we're going to come up with ways to scrub those biases from the data. The point of my talk is going to be that that's not something we're going to be successful at doing, because there are fundamental reasons to believe that this is not a purely technical problem. There are no purely mathematical definitions for what we want out of these algorithmic systems. I'm going to show you that there are different stakeholders here, and they have different criteria that they want out of these systems that leads to different mathematical fairness definitions. And those are going to be simply mathematically incompatible with each other. Faced with that, computer scientists and data scientists are not in a position to make these moral decisions for society. So there needs to be something else. There needs to be a collaboration with ethicists and social scientists and domain experts, people who are experts in criminal justice or housing or hiring and so on, in order to figure out what it is that we want out of these systems. So that's the thing I want to give you as a provocation today. These are super important problems. Of course, we need computer science and data science and statistics, but that's not enough. We need something else. We need a new kind of collaboration, and I want to encourage that. Great. So one reason, by the way, that these questions have become really prominent today is because of a 2016 investigation that ProPublica did. They're a public interest advocacy and journalism organization. They looked at a recidivism prediction tool called Compass. So what is recidivism prediction? You use basically data and algorithms to predict when there is a defendant in the criminal justice system, what is the probability that they will reoffend, that they will commit a crime if you were to give them their freedom. So a lot of algorithmic techniques are being used for that today. If you didn't know that, that might be really surprising to you. I was surprised when I first found out. But not only that, what they found is that the false positive rate, that is the rate at which somebody is falsely declared to be high risk, but it turns out that they didn't commit a crime when you observed them for the next 2 years or whatever, the false positive rate was twice as high for Black defendants compared to white defendants. This was sort of a bombshell story, and there was a lot of discussion around this. The company Northpoint that built Compass responded to this with a 37-page document saying that basically refuting the accusations, and then it led to a lot of discussion, and then a lot of academics got involved. And they wondered what is really going on here, because ProPublica had one definition of bias according to which Compass was biased. And the company had a different definition of bias according to which it was not. So they tried to see, is there a tension here? What's going on? Can we achieve all of these at the same time? And several different groups of researchers proved versions of an impossibility theorem that led ProPublica to post this follow-up article saying bias in criminal risk scores is mathematically inevitable. That sounds crazy. How can that be? How can math be in the way of our efforts to achieve basic social justice? It sounds very unintuitive, and yet it is true in a certain technical sense, and I'm going to show you exactly how that is. So to understand that, let me, just give me 1 second here. Let me show you one way to look at bias in these Compass scores. And that is in the sense of statistical bias. Statistical bias might be something you're quite familiar with, so let's look at it like that. Compass produces a risk score that's somewhere between 0 and 10, but you can sort of scale and stretch and shrink that in order to interpret that score as a probability. So when we interpret that score as a probability, we get a curve that is something like this. This was done in this paper, and you can look at this as a probability density function. There's one curve for white defendants and one curve for black defendants. And so, there's a certain proportion of people who have a 10% probability of reoffending or something like that. So the obvious question you can ask is, are these probabilities accurate? So one way in which you can measure that is you can look at a certain window, let's say around 40%, and you can ask, of the people in that window, when you follow up and see what percentage of them reoffended, is that proportion actually 40%? And when you do that, it turns out that these scores are actually pretty accurate in that sense. They're well calibrated, is what we would say. And this is true whether you look at the overall set of defendants or only the white defendants or only the black defendants. So that is a point in favor of COMPAS. It seems like it is doing something that is accurate and unbiased in a certain sense. But that's not the only concern that we might have. In fact, the question that ProPublica was asking is something quite different. And that can be captured by the notion of group fairness. And what group fairness asks, there are a collection of different group fairness metrics. What they all have in common is they're asking the question, do the outcomes of the system systematically differ between the different demographic groups or population groups? Right? And this is the sense in which the false positive rates turned out to be very different between the different groups. So I want to give you a mathematical understanding of group fairness and why it can be hard to satisfy this criterion sometimes. And I want to do that by showing you a particular impossibility theorem that was proved in a paper by Col de Cobo. And here is a quote from that paper. There are a lot of terms here that I've bolded. I'm going to explain them both intuitively and mathematically, and I'll explain why they're incompatible with each other. If an instrument, that is a risk prediction instrument like COMPAS, if it satisfies a criterion called predictive parity, but the prevalence differs between groups, that is the total, the probability of a black defendant reoffending and the probability of a white defendant reoffending, if those are different from each other, then the instrument cannot simultaneously achieve equal false positive rates and equal false negative rates. So this is the theorem. There's actually a relatively simple proof of this theorem that I want to show to you. And I want to draw some intriguing conclusions from this. Yeah, makes sense so far? Okay, so let's dive in and let's look at this mathematically. So there is a very simple problem setup that leads to this conclusion. It's almost going to look oversimplified, but there is a reason for it. We're going to be able to draw some interesting conclusions from it. We're going to look at essentially a 2x2 confusion matrix, something that you may have seen many times before. So this square represents our entire population, and I'm splitting them into two groups: people who recidivated and people who did not recidivate, went on to commit a crime and did not do so. Yeah, fair enough. So that's on the vertical axis, but also you can look at it in terms of whether or not the algorithm considered them high risk or low risk. And so we can also split it on the horizontal axis, and you have a group of people who were labeled low risk and high risk. Right? So this is the basic 2x2 confusion matrix for any binary classifier. And this is so simple that you can apply it to a lot of different scenarios. And these four groups would be called the false positives, true negatives, false negatives, true positives, and so on. It doesn't matter if you remember the mapping of those terms to those boxes, but the intuitive idea should be clear, right? False positives, for example, this is the one that we're most worried about. We're worried about people who were labeled high risk but did not, in fact, recidivate. So that is a situation that we really want to avoid. So these two are the errors of the algorithm, and these two are the ones that it got right. Yeah. So this is very simplified, but I'm going to show you that it yields useful insights, and also it's applicable across the board to analyze a variety of algorithms. If predictive algorithms for loans and hiring and insurance and so on. If it's loans, this vertical line would be, or this horizontal line would be based loan applicants who defaulted and those who didn't. And if it's hiring, you define a binary criterion: did somebody succeed at a job or not? Okay, makes sense so far. And I want to restate one key assumption is that we assume that the prevalence is different between groups. In the loans example, we assume that the probability of people from one group repaying the loan is different from the probability for the other group. There can be a variety of reasons for that. It could be the result of historical prejudice that leads to differences between the groups. It could be intrinsic differences between the groups in some cases. We don't know. We don't really care as far as the theorem is concerned. This is the basic problem setup. Okay, here's where it gets interesting. I want you to do a thought experiment. With this basic setup, what do different stakeholders want out of the binary classifier? It's when I started thinking about this question that everything clicked for me, and that's actually when I started giving this talk. And this is going to explain fundamentally why there are tensions between the different things that we want. It turns out it's because there are different stakeholders and they want different things. And when you look at that mathematically, based on these four numbers here, it'll turn out that they're incompatible with each other. It's that simple. So who are the different stakeholders? One stakeholder is the decision maker. And this is, this is well explained based on a particular quote I'm going to show that represents the contention between ProPublica and Northpoint, who's the decision maker. Northpoint had a 37-page response to ProPublica's article, and then ProPublica read that and said, okay, yeah, we get it, but things look very different when analyzed from the perspective of the defendants, particularly those wrongly classified as future criminals. So, and it's interesting to see Northpoint's response to this. It's a 37-page document that I think shows an inability to even temporarily take the point of view of the defendants. And I thought that was an illuminating look in why two groups of people reached very different conclusions from each other. So let's dive into it in more detail. The decision maker might ask, of those whom I've labeled high risk, how many will recidivate? So that's the question they're really interested in, right? They made a decision and they want to know how good was that decision. Yeah. So this is a question about predictive accuracy. And this term is called predictive value. And in this matrix, the way we can get that is we only look at the right-hand side of the matrix, only the people who are labeled high risk. And we look at, of the people labeled high risk, how many actually did recidivate, and that is the true positives. So we're looking at the true positives divided by false positives plus true positives. That is the predictive value of the decision. We can also look at it from the perspective of the defendant. The defendant asks, what is the probability that I will be incorrectly classified as high risk? So this defendant is only looking at the top half of this matrix. They're looking at what happens to the people who do not recidivate. And of the people who don't recidivate, what is the fraction who are incorrectly classified as high risk? That is, what is the fraction of false positives? Yeah. All of these are just mathematical expressions that fall out of this 2x2 matrix. And then society might have a different objective. Think about it in the context of hiring, for example, rather than criminal justice. Society might ask, okay, you've selected a set of people using your binary classifier. Is that set of people demographically balanced? And that actually also falls out of the 2x2 matrix. We would simply look at what is the fraction that falls on the right-hand side of this line, and if that fraction on the right-hand side is the same for the different demographic groups, then we would say that this classifier produces results that are demographically balanced. Okay, so the point I want to make is that there are very natural motivations for these various metrics that we might have. I've shown you demographic parity, that's the last one, that's what a society might want. I've shown you the predictive value, that's what the decision maker might want. And there's sort of a converse of that, which is negative predictive value. And I've shown you the false positive rate. Similarly, there's a false negative rate. And you can also just talk about the accuracy of the classifier. So I know there's a lot of terms here, but this is the key point that I want to make, which is there are a lot of stakeholders, there are a lot of different perspectives. And just based on that 2x2 matrix, they might ask for different mathematical criteria because different things matter to each of them. And there's a beautiful theorem showing that you can't achieve any three of these at the same time. There's going to be a little bit of math now, but I'm going to go through that and show you how it works. But hopefully the broader principle should be clear, which is that, so these are the three specifically that I'm going to show you, but it pretty much applies to any three of these. But the broader principle is that different metrics matter to different stakeholders. There's no one right definition for what fairness should mean in this kind of situation. Question, please.
Yeah, so I just have a quick question. You pivoted from bias to now talking about fairness.
Sure.
So from the statistical community, bias is a very specific definition.
Absolutely.
It's not false positive rates, not false.
Totally, yeah.
So the way you're describing to me, I'm not sympathetic to Republicans. They use the statistical word incorrectly. What if you comment on is bias
yeah, that's a great question. So what I was addressing very briefly at the beginning is when we looked at this notion of calibration. This corresponds almost precisely to the notion of statistical bias that you might have. Let's put aside the issue of terminology for a second. I know that a lot of people were offended when ProPublica used the word bias to refer to something that does not map to statistical bias. I think that was a lot of controversy about terminology in a way that didn't really map well to the concerns that people actually have. And so I don't have a point of view on whether it's okay to use the word bias to refer to these other things, societal biases, as opposed to statistical bias. Maybe you don't want to call it bias. I'm perfectly okay with that. The broader point we're making is that when you have unequal false positive rates, you might have disparate impacts between different subsets of the population, and that is something that really feels like something that we should avoid. So that's why these definitions of fairness capture all of these different properties. You might want to call some of them bias and not others. You might want to call all of them bias. I'm not taking a point of view on that. Please.
What do you mean it's not? I mean, things like disparate impact under certain situations are illegal.
Yes, totally.
So I mean, you're using language as if we get to sort of decide. I mean, statistical discrimination in hiring is legal.
Absolutely. And
but if, I mean,
yeah,
we haven't really addressed the question as to whether, like, for example, race is being used in these predictive models.
I am going to get to that.
As opposed to other characteristics which might be correlated with race.
Sure.
I mean, it's perfectly fine to use income or wealth in deciding on whether to give someone a mortgage.
Absolutely.
Even if groups differ in how much money they have. We
are going to get to all six questions.
I won't hire the woman because she might get pregnant. Because women get pregnant and men don't. That's illegal.
Yes, so there were several points there.
Some context.
Yeah, there are several points there. They're all good points. Certainly there's an important concern about certain types of effects that we consider to be disparate impacts being illegal. And that is the motivation for a lot of these fairness definitions. And that is what we're trying to capture. What I was responding to earlier is whether we want to call that a bias or not. And just that point of language is something that I don't have a strong point of view on.
But bias is a legal meaning too. That's one the way it's good. So
sure, absolutely.
ProPublica may be using the legal definition, so it's not bad that they use bias.
Absolutely. So I hope what we can agree on is that certain types of impacts of these algorithms can be illegal and we might consider them unethical. And that might happen even if the algorithm is not exhibiting what we might consider to be statistical bias. And that is in fact at the root, of a lot of these concerns. The way that we had traditionally thought of algorithms being unbiased turns out to be not adequate when we are looking at these social and legal concerns that arise. Please.
One quick comment, because when you are aggregating all of this in AUC and so on, it has been actually known through Simpson's paradox, what is known as Simpson's paradox.
Yeah.
Well, actually, in each of the subgroups, you might have phenomenon, but when you add it up and aggregate them, they're not going to show up at all.
Absolutely.
And so this is one of the big problems in terms of some of the machine learning algorithms.
Absolutely.
Because when you start really breaking down each of the subgroups, you will see immediately the phenomenon of the type that you're mentioning. But when you aggregate, you won't even see it.
I completely agree with you.
I feel that may have something to do with the prediction parity versus the
false positive rates.
Right, because the prediction parity is about the subgroup, whether they're same across, and then the overall is the aggregate part of the
Exactly. That's why I'm saying that this is another issue.
Yeah, thank you. That's a valuable point.
There's one other. So you haven't used the word uncertainty very much.
Sure.
I'm just, wondering if you're going to get to the, the issue of uncertainty.
Yeah.
Assessment.
Yeah, that's a good point as well.
Very high uncertainty, we have any bias, but there was some problem, so to speak.
Absolutely.
Using it at the individual.
For sure.
It's like teacher effects in accountability, that we know that teachers differ in their quality, but models do a very bad job of predicting whether individual teachers are good or bad.
Yeah.
And it's that uncertainty.
Yeah. So just because of time limitations, I wasn't going to address that today, but that is something that is a concern in the community as well. And one way that people talk about it in the ethical sense is fairness versus justice. You could do, you could have a model that has a very high error for everybody. You're treating everybody equally badly in that sense. So fairness might be satisfied, but justice might not be. And yeah, that is an important concern as well. I just wasn't going to say too much about that. But Okay, we're running a little bit behind for a lot of reasons, including the weather. So I'm going to skip a few slides with the proof of this theorem, for example. But the high-level point I want to make is, again, that there are these different metrics. They matter to different stakeholders. We can't simultaneously achieve all of them. And so that means that I'm going to skip this stuff. Yeah, and get to this. And this is the first hard problem that I want to present to you. This is something that the technical community is really struggling with. We know that there are these tensions. We know that there are these impossibility theorems between different measures of group fairness, between group fairness and individual fairness, treating everybody the same way instead of setting different thresholds for different people. And also between fairness and utility, the overall objectives that we might want out of the predictive algorithm in terms of public safety or whatever it is. So having discovered these trade-offs, what the technical community has been doing, the response to this has been, let's formulate each of these in terms of components of a loss function and then jointly optimize that loss function. That's been the approach taken in the technical community so far, and I want to push back against that. It's a little bit like adding up apples in fairness and concluding that the answer is 7.3. There's a certain incoherence to it. There is not a lot of moral grounding. There's not an ethical framework that's being used so far in order to adjudicate between these different important criteria that we might want. And that is one place where I think we have to acknowledge that these are not purely technical problems and start working with ethicists and domain experts in order to figure out what our priorities and criteria should be in designing these algorithmic systems. One quick point I want to make is that a lot of this actually also applies to human decision making. It's not as if we didn't use algorithms, if a judge were making decisions about bail and so on, that none of these concerns would arise. It applies equally well in that context too. A third point I want to make, and thank you for raising that legal issue, by the way, and that's what this gets to, is that there is a tension between disparate treatment and disparate impact. One of the things we've learned pretty strongly from this literature is that if we insist on treating everybody the same, we don't use race as a variable, we set the same threshold for all groups, then we're going to end up in a situation where the end result of the predictive model is very different outcomes for these different groups in terms of different false positive rates, et cetera. And this is a tension that's been already known in the legal community, but I want to argue that it's a much harder problem in the case of machine learning because in traditional scenarios, the approach has been sort of taking case-by-case workarounds, but that doesn't work in machine learning because the whole reason we're doing this is that we want one uniform approach that's going to work across all of these scenarios. So that's another key tension as well. So getting back to your question of, did the model actually use race as a variable? I have perhaps something surprising to offer to you on that. People have tried to quantify how much does it help fairness to avoid looking at race as a variable. I'm going to show you a graph that gets at just that. So this is from a paper, and here's the reference to the paper. What they're looking at is a loan application prediction scenario. This is based on FICO scores and various other variables. And in their data set, there are 4 racial groups. And what they're looking at is under various predictive models, what would be the success rate? What would be the loan application probability for each of those demographic groups? Now, one thing you can do here, of course, is that you can constrain your model to say that each of those groups should have the same success rates. And if you do that, you're going to get something close to 50% for each of those groups. Or you could have a completely unconstrained model that says, I just want to maximize profits. And then you get a very wide spread of success rates here, ranging from a mere 25% for one group to well over 80% for another group. Here's the key question. If we built the model so that it doesn't look at race as one of the predictor variables, are we going to be close to this situation or are we going to be close to this situation? Let me show you what happens. We're actually very close to a completely unconstrained max profit classifier. So what this means is that something, and these are other different fairness criteria that you can apply, but this second row is the key thing I want to show you here. So what this means is that something that we've long thought of as a very important and key fairness technique, which is not using the protected attribute in making decisions. In the machine learning context, that ends up doing almost nothing for fairness. It's almost as if you impose no fairness constraints at all. And this has been a somewhat surprising finding. So why is it that in the machine learning context, blindness to the protected variable is so ineffective compared to human decision making? I will offer two possible reasons why this might be the case. One is that in machine learning, bias is just a side effect of maximizing accuracy. The model is not, does not have an intent to discriminate, right? Of course it doesn't. That's not what's happening here. It just turns out that all the variables are correlated. Race is correlated with a variety of other things that you might want to use for making your predictive decision that ends up having that effect anyway. And also machine learning is much better at picking up on these proxies and correlations in the data. If you gave a human a data set and you withheld race, they wouldn't necessarily be able to infer it by looking at all of the other data points, but machine learning models are really good at doing that. Yeah, so this means that if we want our models to avoid disparate impacts, we actually have to start putting in race as a variable into those models. In order to avoid disparate impacts, we need to practice disparate treatment. This has been one of the strongest conclusions of the technical literature on fairness in machine learning. And this leads to another reason why this is not a purely technical problem. If we want to do that, we immediately run into legal concerns and ethical concerns. So we'd better start talking to lawyers and policymakers and social scientists and ethicists about how we're going to resolve these dilemmas. So that's one of the key insights that I wanted to leave you with. So, and there are various other interesting issues. I think there's an argument that a randomized classifier cannot be fair, that you're flipping a coin as part of the making a decision. But there is another argument why only a randomized classifier can be fair, because a deterministic classifier is going to have this very sharp cutoff. If you have a 51% risk score, you get one decision. If you have a 49% risk score, you get a totally different decision. So these are all other ethical conundrums as well that we don't have really good solutions to.
And also, I feel the answer will be different for group fairness and individual fairness.
Definitely. Yeah, that's a good point. Thank you. Okay, for the last 10 minutes, I want to pivot to a very different set of concerns. They're going to lead to hard problems number 2. Tin, you want me to finish at 1? Is that a good turn?
We have the 1:30.
Have the room until 1:30? Okay, so maybe I'll speak for another 15 minutes or so, and then we'll take questions. Is that okay with Ms.? All right, so I'm going to pivot to a new set of concerns now. So far, we've talked about hiring and criminal justice and all of these consequential decisions about people. I'm going to show you another example, another set of examples of bias that are going to look very different. And I want you to think about how is this different from all of the examples we've looked at so far. So here's the first example. There's an app called Face App that you can use on your phone. And it has various filters that you can use, fun filters that you can put on your images before posting them on Instagram. One of the filters of Face App was something called the hot filter. And what do you think the hot filter did? And remember, this was trained using machine learning based on what previous users had rated as hot people versus not hot people. It turned out that what it picked up on is the hot filter ended up lightening people's faces. Right? Not horribly surprising, but very disturbing. Yeah. So this is another example of what people have considered to be bias in these machine learning algorithms. So you can see that there's a difference here from what we've been talking about. Here's another example. There's an online tool called Perspectives, which is apparently a toxicity rating system to filter online comments and rate them for toxicity. And somebody tested that with various kinds of words that you might think of putting into it. And here's what they found. I am a man. I had the lowest toxicity score. And over here, you can see what got the highest toxicity score. So in another sense, it seems to be reflecting societal biases and stereotypes. It seems very uncomfortable. We feel like this shouldn't happen. But can we clarify what is going on here and exactly why we consider this unacceptable?
Can you tell us how it's trained? What is the dependent variable that it is using?
Yeah, I think what it's training on is what comments that people have in the past rated as, I don't want this on the site, something like that. That's my guess. What's that?
Wikipedia pages.
Wikipedia. Oh, I didn't know that. Thank you.
Yeah, I know, it's really fascinating.
Wow. Let me show you one more example. This is an image search results for a CEO. And, it shouldn't be that surprising, but also it's a little bit disturbing. So, we've always had concerns about how's the media reflecting our world and stereotypes in mass media. But now that role is being partly played by AI and machine learning algorithms. So what are the types of inputs that children, for example, are exposed to? So these are the concerns that come up. And so this is another thing that people mean by bias. They're all very different meanings of bias, but let's try to get at what is the key difference between this and criminal justice and so on. Because it's not as if anybody's being denied a CEO job because of these images. It's not the same kind of concern, but it seems to be something else. So this was beautifully explained by Kate Crawford in her NIPS keynote. What she says is that the difference we're looking at is allocative versus representational harms. Allocative harms are the ones we've been talking about in the first part of this talk, where a system withholds opportunity to someone. Representational harms are things that reinforce these class differences or group differences in some way by stereotyping or cultural denigration or underrepresentation of a group in a system or a model or a data set. There are a variety of differences between them. These you can see through an economic lens, and so it's much easier to formalize. They correspond to discrete transactions, and they have these immediate effects. On the other hand, representational harms are more social and cultural in nature, and they have these diffuse long-term effects. So it's not quite as easy to formalize exactly why we consider this troubling or wrong in some way. So we wanted to study representational harms in a paper. And so what we decided is that instead of looking at these individual examples, if we want to get a full understanding of how machine learning technologies pick up these representational stereotypes from our culture, then we should look at something that has a wide spectrum of representational ability. In other words, let's look at a machine learning model of language, and we can query it for all kinds of biases, because when we have language, we have semantics, we can ask it questions. So that's what we decided to do. And specifically, we looked at word embeddings. Who's familiar with word embeddings? Just a quick show of hands. Okay, about half the room. Let me give you a very quick analogy. What word embeddings are a way to automatically map each word in the language to a vector in something like a 300-dimensional space in such a way that similar words are mapped to nearby vectors. So let me give you an analogy in a 3-dimensional space. In this room, for example, you might put cat and dog and other animals over here, and you might put maybe love and other abstract emotion words over there. But the idea is that this captures a lot of the relationships between words, and machine learning methods are able to use these representations to do a primitive form of reasoning about words and concepts in language. So let me show you a visual representation of this. And this is in 2 dimensions. What you're seeing here is pairs of words that are different only in terms of their gender. For example, brother and sister, woman and man, et cetera, et cetera. So it's pretty cool that the system is able to automatically learn these vector representations of words. And this is a 2-dimensional projection, but this is actually happening in 300 dimensions. So what this means is that you can, for example, automatically answer word analogy questions. You can ask it man as to woman as sir as to what, and it'll do a little bit of vector algebra and come up with madam, because that's the closest word to that vector operation. Does that make sense?
How does it come for context?
Say that again, please.
How does it come for context?
In other words, words that have 2 different meanings. So in the simplest version of word embeddings, and this one in Globe, for example, they just get mapped to the same vector. But there are newer techniques that actually resolve the different senses of words and map them to different vectors. And context is determined by looking at the words that appear nearby. And so the idea is that words in different senses are going to have different neighboring words when they appear in context. So that can be done automatically. But think about this. What do you think would be the result if you asked it man as to woman as doctor as to what? Any guesses?
You get nervous.
Nurse, exactly, right? So that was our observation that we started with, and others had this observation as well. So we realized right away that these vector representations are actually really good for capturing these societal stereotypes. And so we wanted to ask, how deep does that go? How much of these societal stereotypes are actually captured in these things? And so we knew we were going to be able to measure cosine similarities between pairs of vectors. So that kind of tells you how similar different words are. So this was a starting point for understanding if these societal biases are captured, but we needed something else. We needed some definition of what are the societal biases that we're looking for. We didn't want to be the ones to come up with that ourselves. But luckily for us, that's been done over the past 20 years or so by psychologists and cognitive scientists in something called the implicit association test. This was a key thing that enabled us to do our study. And if you haven't heard of the implicit association test, I encourage you to go online and take it yourself. I remember when I first took it, I learned things about myself that I didn't know. And let me tell you why. Here's what the implicit association test does. Here's a visual of somebody taking the implicit association test. What's going on is that this test taker is asked to classify this word, the stimulus, and is asked to push the left button if it's either a boy name or a math word, and the right button if it's either a girl name or a reading word. What's the idea here? If it is true that this person has a stereotype in her mind that boys are good at math and girls are good at reading, then this task is going to be intuitive and easy because it corresponds to the stereotype, right? There are a variety of stimuli coming one by one, and she's asked to do this as quickly as possible. On the other hand, she will also be asked to do the other version of this, where it's the left key for boy names or reading words, and the other way around. And so this one we say is stereotype incongruent, and this one is stereotype congruent. The hypothesis is that the stereotype congruence task will be faster, slightly faster, maybe just a few milliseconds faster. But in fact, when you do this test over and over again, and when you look at the differential reaction time, that turns out to be a good quantitative measure of bias, of an association between two different concepts in somebody's mind, or you can do it in aggregate for the whole population. So, yeah, please.
So how do you know if the user is interpreting the language in the same way? So what if we're both looking at boy and we have a different interpretation of boy? How do you account for the nuance in language?
So they're not actually looking at the word boy, but what they're doing is they're classifying these words, boy names like David and so on. You know, there are certainly concerns about what is the implicit association test actually measuring. There's a lot of literature on this. There are certainly debates about that. I don't want to claim that it's there's a completely uniform interpretation of what it means, but we do know that statistically, when we do these tests, we get these curves where there is in fact a separation between these two. And this is pretty stable across different individuals in the population. And you can actually use this to get an effect size, and you can use that to get a quantitative measure of bias. And there's been a lot of literature on that, and that has been pretty successful.
But you know, there's a difference in having a stereotype and being aware of stereotypes.
Exactly.
If you said man is to woman as doctor is to, and I said doctor,
yeah,
we would have, oh, I know what you wanted me to do. You wanted me to say doctor, nurse.
Right.
But it's a that I think.
Precisely. So that is why they designed the implicit association test. It's supposed to get at these unconscious biases.
What awarenesses of biases in the world. I'm just thinking there's a distinction here.
I completely agree with that distinction. And this is trying to get at the unconscious biases. That's my point. Okay. Yeah, so this difference in distributions tests the hypothesis that these subjects have a particular implicit association. So what we came up with was a version of the implicit association test for machine learning. It's very similar. We just make a few tweaks. So for the incongruent pairing, for example, we would look at the similarity between a basket of female names and math words, and then we would subtract the congruent pairing from it, female names and reading words. And over here, we would do the other way around. That would give us two distributions, and we would look at how far separated are those two distributions from each other when normalized by the standard deviation and all that. And that gives us an effect size that's Cohen's d, and we compare this to the human testing results. So one question you might have is these word embedding models, how are they trained, how are they built? And here's what we did. We looked at pre-trained models. These are standard models that have already been trained and are widely distributed and are used in all kinds of machine learning applications like natural language translation and various other things. This one, GLOVE in particular, was by Stanford. It's a state-of-the-art project. It was trained using a crawl of all of the text on the web. And if you don't know how these word embeddings are typically built, this is the normal thing to do. And that might be a little bit surprising to you. Why would you train these word embeddings using just unfiltered text found on the whole web? And in fact, funnily enough, our paper was on Colbert, and Colbert had the very same question. AI gleans the meaning of words by analyzing text. So programmers did the worst thing possible. They fed it text from the internet. He was very confused about this. This sounded like a stupid thing to do. However, that is exactly how today's state-of-the-art natural language techniques are trained, using essentially unfiltered text from the web. And that's how computer vision techniques are trained, using all of the pictures from Instagram that everybody uploads. So that's an interesting question to ask. Is that the way we should be doing things, or should we be curating these data sets? By the way, I should quickly note that we did find that when we repeated this with the Google News corpus, we got almost exactly the same results. So in this case, it wouldn't have made a huge difference, but it is something to keep in mind. Where we get our data from might affect what sorts of biases and stereotypes get into them. But very quickly, what we found was we started with some universal biases in the human implicit association test. People rate flowers as pleasant and insects as unpleasant. We definitely confirmed that in our findings, and we can quantify that with an effect size and a p-value. We can talk about details later if you like, but the high-level point is that we were able to confirm these stereotypical associations. The more interesting ones are things like the valence of race-specific names. That is, some names are much more likely among European Americans, and some names are much more likely among African Americans. And in the human implicit association test, we have this disturbing finding that there is an association between these and pleasant words, association between these and unpleasant words, and we find exactly that with our machine learning models as well. And again, you see pretty high effect sizes. An effect size of 2 is the maximum, so this is considered a huge effect size, and we have very strong p-values for this as well. Julia?
What happens if you ask humans in the African American category?
Yeah, so there are studies on that, and so there are 2 conflicting principles that explain the strength of human biases. One is in-group, out-group, right? So that would predict that those biases would be lesser or reversed. But there is another principle, which is internalized oppression is one term that is used for it. So internalizing the prejudices of the majority group. So that would predict that the biases would still be the same among respondents from the minority group. So what we see in practice is some complex combination of these 2 effects. That is my interpretation of the psychology literature. Obviously not an expert on that. We also confirmed various gender stereotypes, like female names being associated with family words, male names with career words, and also science words with male words, arts words with female words. All kinds of stereotypes that have been tested in humans, we were able to confirm in these models as well. And we tested a few others: age, physical versus mental illness. Everything we tested for which we were able to find these input lists of words, we were able to confirm with state-of-the-art word embeddings that are used all over the place in these NLP technologies. Now, here's something you might say, and this is an important question to ask. So we're finding these stereotypical associations. Maybe those stereotypes are just coming from empirical regularities in our real world, right? And so maybe what's going on here is that there is no statistical bias in that sense. What the models are doing is capturing what's the state of our world. So we tested this. One way we tested this is we got data from that's published by the Bureau of Labor Statistics for various occupations and the percentage of women in those occupations in the United States. So I'm going to show you a graph of what that looks like. So on the x-axis here, you see each dot is an occupation, and the percentage of women ranges, there's a wide spectrum here. And on the y-axis, what we decided to test was, how does this compare to how feminine does the word embedding think that particular occupation word is? And we were shocked by this. We thought there would be maybe a 10%, 20% correlation, but you actually get 90%. What that means is that the word embedding is very good at picking up from completely unfiltered text on the internet this very fine-grained information about 50 different occupations and what is the percentage of women in each of those occupations. Right? So at least in some cases, at least for these gender stereotypes, what's going on here is very much mirroring something that is happening in society. So in a sense, what you're seeing here is a lack of statistical bias. In a sense, if you're a good statistician, this is exactly how you would want your model to behave. If it didn't capture these regularities, you would think that it was missing something, that it's not reflecting the real world and it's not reflecting language in some way. So there's a tension there that I want to point to. And similarly, another thing that we found, we also tested, it's really good at picking up for androgynous names that can be given to either boys or girls. It's pretty good at picking up what is the percentage of people with that name who are men versus women. So there's a lot of empirical regularities that are getting picked up in this data. We tested things like participation of women in Olympic sports in different countries. All of that is coming through, so it was pretty interesting. Now, but here's the key point. So even though this is in a sense statistically unbiased, when we take these models and put them into applications, it could produce results that we're very uncomfortable with. Let me give you a simple example. This is Google Translate. Here's what happens when you start from these sentences. She's a doctor, he's a nurse. Translate it to a language that has gender neutral pronouns. O stands for both he and she, and then translate it back to English. Right, gender's reversed. But this is exactly what you would expect from the statistical patterns in text. The first sentence has been observed in the training text a lot more often than the other sentence, she is a doctor, right? So this is a lack of statistical bias, and this happens for most occupations, other translation engines, other language pairs, and so on. But it leads to effects that we consider to be undesirable in these applications. Let me give you another example. These are pretty easy to find, and I encourage you to test some of these online applications yourselves. This is from an image labeling application. I'm going to show you how Google labels a picture of HP CEO Meg Whitman. It automatically comes up with various labels, and there's a bunch of these labels. Try to see if you notice something fishy. So here are the labels for Meg Whitman. Anything surprising in there?
Sorry, what would be the percentages represent?
Percentages are, confidence scores. How likely is it that this picture represents somebody getting an award? Yeah.
I mean, there's no CEO.
Yeah, of course, right, sure. There's no CEO, but perhaps more surprisingly, what is singer-songwriter doing here? Why do you think it's saying singer-songwriter? Any hypotheses? Yeah, very good. So this is from a paper that I'm working on with Kate Crawford and others. And so we haven't confirmed this yet, but we do have statistical significance, by the way. We tested a bunch of male CEOs and female CEOs, and consistently you get, in a significant fraction of cases, you get singer-songwriter. You never get that with men. Our hypothesis is that in the training data sets for this image annotation engine, of the women that it has seen standing in front of microphones, overwhelmingly it's been a case of a singer, and so it's picked up that association from the training data. Question, please.
There's no gender, it says person, but.
It says person, yeah. Yeah, presumably a human has edited those labels to be gender neutral, right?
So it seems that there's some features deliberately hidden from the label.
Quite possibly. Quite possibly. But clearly that little bit of manual intervention is not at all sufficient to edit away all kinds of patterns that might be in the data set that we might not be comfortable with. Yeah, so this is the crux of the second hard problem that I want to give you, which is when we say bias, coming back to your question, it could refer to a variety of things. It could refer to something that is universal and problematic. Flowers are pleasant and insects are unpleasant. It could be something that's clearly prejudiced, different valence between black sounding and white sounding names. It could be something that's reflected in empirical statistics like gender and occupations, right? The problem is there's no way to algorithmically distinguish between these. And these are just 3 examples, but there are an infinite number of such stereotypes that are embedded in our training data sets that are gigabytes and terabytes today. And so, yeah, we don't know which of these categories we're in. And even if we look at one of these categories like these empirically true stereotypes, we're going to have a hard time knowing if it's desirable or undesirable. I can easily come up with an example. Let's say we're analyzing historical job ads and trying to see if more men or women were in that particular job category. The kinds of stereotypes that I've shown you would be exactly what we want as knowledge from our data sets in order to do that task. Whereas in another application like translation, it produces results that we're not at all comfortable with. And so the key point that I want to tell you is that this notion of prejudice, unlike statistical bias, which we're more comfortable with, this is something that is a cultural notion and it is constantly evolving. And if we want to mitigate these societal biases, we might want to inject statistical biases into our models, which sounds like a really weird thing to do. And also, we just don't have clear definitions of what is desirable and what is unacceptable. So that's the crux of hard problem number 2. It's basically what I've said so far.
When we're injecting something back, we don't call them bias anymore, we call them calibration.
Yeah, that's a fair point. Question, please.
One question. This is really amazing and impressive. First of all, I was wondering whether if you were to break down this data set by year and try to look at whether embeddings are changing from that perspective, and whether we as society are evolving in terms of dealing with our biases, that would be really fascinating.
That's an excellent question. So there's a paper that sort of does something related to that. What they have done is they looked at how these word embeddings have changed over the decades by training different word embeddings on, I think it was the Google Books corpus, which is a historical corpus going back like 2 centuries. They didn't specifically look at these biases and societal stereotypes, but they looked at how the meanings of words have changed. For example, how the word gay changes from primarily referring to happiness to primarily referring to sexual orientation. So those are things that we can pick up using these historical corpora. So I think it's a powerful technique. It hasn't yet quite been applied to these notions of biases. So I'm going to stop here. I had a few more slides, but I just wanted to put up some high-level takeaways here. What I hope I've shown you so far is that there's an emerging consensus that our data that we're using is going to have inevitable biases, and therefore the predictive algorithms that we're using should be able to account for them in some way to mitigate those biases. And this calls for new research and new science. But there are hard problems in trying to do this. These are not purely technical problems. One is that there are these impossibility theorems. There are trade-offs between the different fairness notions that we want. And purely as technologists, we're not going to be able to resolve these. We need ethicists and social scientists and domain experts to weigh in. And the second is, as I've shown you, in the domains of natural language processing and computer vision, there can be all kinds of stereotypes that are embedded in the data. We're never going to know just algorithmically, statistically, what's okay to keep and what we need to scrub from the data. So again, we need something different. We need perhaps a way by which a human expert, a linguist, or somebody who's an expert on hiring can specify what is the historical context for this decision, what are the ways in which people have discriminated in a particular domain, and that needs to be taken into account when you're defining what is a bias and what is not a bias. It cannot be done in a purely mathematical way. So that is my provocation for you. There are these super interesting and exciting problems. Of course, we need technologists to be working on these, but technologists by ourselves are not going to completely solve these problems. We need new structures of collaboration. That's my high-level takeaway for you, and thank you very much for listening.
So the top series here is from 12 to 1:30, so we need enough time for further questions.
Right.
Yes, a question about, so at the HCI conference a few years ago, there's a great paper that was highlighting that disparity in image search results.
Yes, Matthew K. and others.
Yes,
yeah, I know that
exactly.
paper well. Yes.
So they raised the issue of like, what about, so there's users themselves rate image search quality better when those stereotypes are present.
Absolutely.
Yeah, and so then there's this call to action, not among like us as researchers, practitioners, but also end users. Do you have any comments about how to motivate that? So if we do make systems that are more fair, so to speak.
Yeah, for sure. So there are two sorts of questions there, right? Machine learning systems today learn from user feedback. That is considered to be one of the important ways in which these systems can improve. But anytime you're learning from feedback, you get into a number of tricky issues because you're making predictions and the results of those predictions are somehow feeding back into your training set, right? So that issue arises not just in image search, but in a variety of things like predictive policing. There have been a number of papers recently that look at how commonly used predictive policing systems today are not carefully designed. And so, you make a prediction about where to put police officers, and that in turn affects the data set that you use for training your predictive policing systems in the future. So that could exacerbate various feedback loops that exist in society. And certainly in image search engines as well, or even in text search, you produce a result that conforms to people's stereotypes of CEOs being men, and people click on those in a way that conforms to that stereotype, and you're learning that signal again, and you're in turn reinforcing that stereotype in people's minds. And so I think this parallels the discussion that we've had in other domains. Should mass media reflect the stereotypes that exist in our society, right? If you had a movie where the occupational demographics didn't mirror our society, then people would find that unrealistic. They would not watch that movie. So mass media has often felt compelled to reflect these stereotypes, perhaps even exaggerate these stereotypes. However, there has been a big movement, as you might know, with movies and other media pushing back against these stereotypes, finding some medium between, reflecting reality, but also mitigating or avoiding the exaggeration of those stereotypes. And I think in the future, it doesn't quite exist yet. I think there will be a similar movement for machine learning technologies as well. And so I think it's good for technologists to get ahead of that and start thinking about what are the trade-offs, what are the levers that we can play with. Please.
So I know this is down the line, but I'm wondering if you could paint a picture a little bit about what, once collaboration with emphasis as a scientist starts happening, how do you start to incorporate that into these models?
Yeah.
Is it a weight?
Yeah.
Bias?
Yeah.
This kind of weight? How do you pursue that action?
Yeah, that's a great question, and I have an example for you that I hope will be interesting. In the criminal justice context, right, we talked about 6 different fairness metrics that you might have. But here's the question that's not being asked when technologists are just adding up the values of all these fairness metrics and computing a total. The question that's not being asked is, what do we consider to be the purpose of the criminal justice system? And of course, there's a tremendous amount of literature, right, from philosophers and others on this. At a very broad level, I'm not an expert on this, but my understanding is that the purpose of punishment could be incapacitation, preventing that person from being out there and committing another crime. It could be retribution, just punishment for the crime. It could be rehabilitation, enabling that person to turn their ways and get back into society. Or it could be deterrence. It could be a way of disincentivizing future crimes. Now, I would consider it obvious that the ways in which we should weight the different fairness criteria, let's say, should critically depend on what the purpose of punishment is. Because if you're merely trying to incapacitate someone, then you don't have a rehabilitative purpose, you don't have a retributive purpose, then certain criteria don't matter and other criteria matter a lot more. But what is the mapping between these? Nobody has done that work, but that is the kind of work that I hope can happen. That was a trivial example, but I think there are much more profound things to say in terms of how our philosophical theories of justice should help us adjudicate between these different criteria.
So one thing that's confused me is the difference between decision-making and predictive algorithms.
Oh.
So I wouldn't advocate for, you don't want to predict the world as you'd like it to be, you want to predict the world as it is. So when it came to the ProPublica, they were giving prediction scores for the probability of recidivism.
Sure.
They weren't saying you should use this to necessarily just it.
Sure.
It seems like.
Sure.
So it seems like the things you were talking about are decisions that would make with the predictions versus maybe here you mean predictive to mean including the decision.
Yeah, no, that's a great point. And I think that's at the root of some of the tensions here, which is that a lot of the criticism of these predictive algorithms is coming from people who want to use them to predict the world as we want it to be. And that's a tension that we cannot escape. Some people think that we should predict the world as it is, and some people think we should predict it as we want it to be. And I can't adjudicate between those views. But to the extent that there is a concern in society that we should use it in a different way, I think technologists need to start looking at how can we tweak our algorithms and models to make that possible, because that kind of theory doesn't quite exist today. We're really good at predicting the world as it is, but not at incorporating people's preferences and where we want to go with these models.
I feel like, so people usually refer to algorithm have biases, like if the algorithm is not working in the way we intend them to work. But the reality is the algorithm is working in the way we intend them to work under some loss function or target function. It's just those loss function, target function, and training data is not really conforming to the most desirable fairness
Sure.
definition. So therefore, the interoperability and transparency of the algorithm is not really the same about reducing biases from the algorithm.
I mean, it seems that what we need is some kind of diagnostics or warning messages when these predictions are not reliable. For example, the Google Translate thing, like, should have had a warning, you know, where it's ambiguous whether it's a he or she.
Yeah.
But you know, it seems more likely to be a he.
Sure.
You know, based on what you usually see, right? So is there effort towards like throwing these diagnostic and these error messages that would, you know, between prediction and decision? Yeah, that's an excellent suggestion, and that is something that I've actually talked about with people at Google. I think you know, I'm not claiming that I know what Google engineers are thinking, but my general sense is that there is a lot of resistance to move away from this purely automated model. The abstraction that you have input text and you're going to do something purely algorithmic and produce output text in another language is so convenient and aligns so well with business objectives that there needs to be a lot of pushback if you want engineers and tech companies to move away from that. That's my sense. If you're going to involve the user in saying you have to spend extra cognitive effort to look at what the algorithm has produced and to see if that's acceptable to you or not, that really changes the implicit contracts between the tech company and the user of the system. And so I think there's some resistance to that.
I think for the Google translation problem, that's only an indication whether something is a direct translation or something is a speculation or prediction. Right? I think that the word doctor is translated as like a translation. There is no really ambiguity there, but the pronouns are being translated based on prediction. So if a single label that this is a prediction and this is a translation would make a whole lot difference.
I think that's a fair point, but I think even to distinguish between those two would require further research. It's not obvious how to do that today. It might be doable.
You probably need like a pedantic mode, right? That's like, so the users, right? Because it's going to screw users at some point, right? Not if they're not transparent about this.
Sure. A lot of hands. I don't know. Julia, please.
Sorry, you just need to comment that fairness and bias are extremely important, but transparency somehow supersedes them.
Yeah.
What we need to be careful about is to distinguish between the beliefs that we want to be predictable, how it is, or how we want it to be, and then the mechanisms that we're deploying to be consistent with those beliefs. So, because of all of these impossibilities, it's really just extremely important to be able to show what are the assumptions that our system needs.
Thank you.
So maybe a little bit of follow-up to that. It seems to me that one of the issues underlying some of these decision analytics, including some of what goes on in Google Translate, like classification, and you see the output, but you don't see the confidence, right?
Right, exactly.
And oftentimes, we're all going to the doctor and someone's recommending something to us, and we don't know if we're right in the center where lots of people in the studies look just like us, or if we're way down at the end where we're getting a lot of sort of inferred evidence, right? So it seems to me that there's room and a movement for sort of, I think, practices of more transparency, and where that can, there are probably a whole variety of realms where those standards could start being advanced. And I was wondering if you have thoughts.
Yeah, and let me clarify. I am completely on board with you on the importance of transparency. And in fact, this community calls itself fairness, accountability, and transparency. That is one of the three key legs. It was purely for reasons of time limitation that I chose to focus on the fairness side of things. But yes, I think when your automated system is resolving between different moral criteria that different people have that are not necessarily compatible with each other, there's not going to be this kind of fairness solution that everybody can agree on. And so without transparency, we're not going to get very far. Yeah, just vehemently agree.
Yeah, but even I mean, my hope might be there were things outside the fairness realm where maybe those standards could start getting advanced. So fairness where we have value judgments implied, I can see it being more controversial, whereas some other places, it might be the better place to.
I saw your hand for a while.
Great. So first of all, thank you so much for this talk. I've been following your work for several years now, and it's a real pleasure to see you give a talk in person. So the thing I want to press upon here is something that's sort of buried in your talk. So one could say, of course, Google Translate is super biased because it was trained off Wikipedia pages initially, and like, of course, like if you ask any historian, they'll be like, of course language is gendered.
Right.
no surprises, right? And
Totally.
you make that same argument in every one of, I mean, this is a really wonderful talk. You've gone through like a list of greatest hits of, examples of bias in the way that I think fairness, in the way that community articulates this. But you could just say in every one of these cases, well, the training data you took was terribly bad. And this isn't like an artifact. This isn't like an aberration, right? If you go back to like the 50s and 60s and 70s, people doing self-identified machine learning research, right? The whole problem is we can't find agreement about whether we're making progress or not because we're all using different training sets. So at some point, everyone sat down and said, okay, we're going to get funding, you have to use the same training set. And now, of course, people are realizing, oh, these training sets are terrible, right? Like they're wildly biased in all kinds of ways and very easy to show this. So could you talk to, as one way of tackling the problems you addressed today, as like looking at the training data itself, the biases, like are there discussions, interdisciplinary discussions about what training sets are being like used and selected?
Yeah, great question. And I think I had a slide about that I skipped for reasons of time. These conversations are very slowly happening. When I proposed this at FatStar last week, it was considered quite controversial, but I hope that we'll get to a point where this will become the default. I think when somebody curates a training set, they should be required to do a bias assessment, publish an analysis of what kinds of stereotypes are captured in their training data set. Some understanding of the provenance of the data, where it came from, what was the process that generated the data. Today, that is not considered part of the ethical or technical requirements of putting out a data set. Further, we have the issue that not only are these training data sets getting standardized, models are being pre-trained on them, and those are being widely distributed. You don't even need to interact with the training data anymore. You don't need to look at the Wikipedia data set. You don't need to look at the image corpora, ImageNet that are being used. People have pre-trained models come up with these word embeddings or come up with, in the ImageNet context for the machine learning people, transfer learning has been extremely successful. You train your model to predict different object categories using ImageNet, and then you chop off the final layer if you're a neural network, and you take the n-1 previous layers. That acts as sort of as a vector representation of any image that you might throw at this model. And so it is that embedding that is now being distributed, but the embedding you're distributing is not purely a technical artifact, it's also a cultural artifact. It captures a lot about what is going on in our society. So I think there should be some responsibilities for understanding, when you distribute one of these artifacts, what is actually in there. I think that would be a first step. There's a lot farther we can go on that, but this seems like low-hanging fruit, a pretty easy win that we can start with. Oh my God, so many hands. Can you moderate? I don't know how I feel.
I think we can just take one last question and then feel free to come afterwards.
What does your research mean for the researcher? There seems to be language for categorizing or discussing the work is that bias is something that happens in data, bias is something that happens in algorithms, but what if a researcher themselves unable or unwilling to address their own bias as a psychosocial process? And so how do we mitigate those issues?
Yeah, that's an excellent point. I think this gets to a couple of debates that are going on in the community. How important is, for example, the demographic diversity of the tech community, right? If we make progress on that, are we going to make progress on these issues? Or regardless of whoever the engineers are they still going to be stuck with these data sets that incorporate societal biases? I don't know the answer to that, but I think we definitely should work on the demographic diversity of the tech community and also just an awareness of these issues among engineers. For example, I think it should be standard for every engineer doing machine learning to take an implicit association test and understand their own biases. I can't promise that that'll lead to improvement on these concerns, but I think it is something we should be doing. And a second aspect of that debate that is going on in the community is whether we should come up with these fairness definitions and metrics that assume that the decision maker might be acting in bad faith, right? So should we come up with compliance rules so that as long as the decision maker complies with them, we can be confident that these disparate impacts don't exist? Or is the purpose of doing all of this research to come up with ways that a fundamentally benevolent decision maker can analyze their own systems and try to improve them on the axis of societal bias. That's also a debate that's going on. I don't know the right answer. It might entirely depend on context in the particular application. I'll stick around, certainly. You know, I'm here for the rest of the day, and so I'm happy to chat more with all of you.
Okay, so I'm gonna end the formal talk series, and let's just send our speaker again.